Today I'm going to talk about rheology, and most of you have probably not heard of rheology before. I studied a master's in engineering physics, and rheology was not the biggest topic there either, so it's a bit, it's not so unheard of. Still, it's a discipline of its own. If you look it up, it says that rheology is the branch of physics that deals with the formation and flow of materials, both solid and liquid. So it's something in between solid and liquid all the time, but it can be anything from food to asphalt to blood, everything that is not really solid or not really fluid, somewhere in between. And there was a Greek philosopher 500 BC who said that everything flows. You just have to wait, but I'll come back to that. So I have some things to remember this by. So I will talk about different terms and part of rheology that could be good to remember. So what you should remember it by is, I hope the Japanese words are correct. A kind colleague, Ruri Hidema in Nagoya, helped me translate, so I hope it works in Japanese. So if you remember, this is oil, this is olive oil. You have a spring or rubber band, which is elastic. Then you have something that flows but is thick, condensed milk, or like you have some dessert, most of the foods actually. Then toothpaste is a good example. I'll come back to why. And then a yogurt. And then, of course, last, natto. I'll come back to why this. But if you remember these different things, you have something to remember the different terms of, because thixotropic is not very obvious. But first, 3 slides of basic terms. And I've skipped most of the mathematics, because I don't think you are very much into mathematics. So shear is this movement. Extension is this. That's not so difficult. If you imagine a shear flow, if you have 2 planes, then you have something in between, and then you push the force in the plane, that's shear. And the resisting force is what you work with. But you can also have this like in a tube. So if you imagine you have concentric cylinders moving here, because it moves fastest in the center and slowest at the corner. And that means between these concentric cylinders, you also have a shear. So in tubes, you have shear flow. It can be a pipe, or it can be the throat. And then extension. A fluid can also extend. Like when you swallow something, you push it into a narrow channel, then it has to extend. And it will also try to resist the extension. Like here, if you push it through a funnel, it has to extend a lot. So that's extensional flow. So you have both. Okay. But usually, in most situations, you only deal with shear flow, unless you have something which is elastic. But I will come back to that. So the first important term is viscosity. So viscosity describes how thick something is. High viscosity, it's a thick fluid. Low viscosity is like water. And you get it by, this will be one of the few equations. So shear stress, you measure this force, and then you divide it by the area, because then you can apply it to which area you want. And then the shear rate, that is how quickly this moves. So it's like a speed. Imagine that you stir something, that is high shear rate. So if you divide shear stress with shear rate, you get viscosity. And you measure this in Pascal seconds, or still you can see poise or poids, which is an older unit that is still used. Okay, so a Newtonian fluid, it's this one. And this one has a constant viscosity, no time dependence, nothing is happening really. And it could be a dilute solution, water, oil, honey, syrup. And this is quite boring if you're a rheologist, because it is just constant. But it's good to remember one of the extremes. And you measure it usually in this way. You fill your fluid in a cylinder, you put another cylinder in between, then you rotate one of them, and then you measure the force that is transmitted to the second one. So this is like, if you have a thick fluid, this will move more, and then you can have a high reading of the viscosity. This is just the principle. In reality, it's of course a lot of electronics and sensors. And then viscosity of different materials, it can vary a lot. I mean, if you can even have viscosity of air, but it's very low. Water is important. That's 1 millipascal seconds at 20 degrees. That could be good to remember. But then you go up to olive oil like this one. It's a bit higher. And then you go to the very thick things like bitumen, that is asphalt. It's extremely high. That's the active polymer in asphalt.
Oh, okay.
And there, I usually get the question also about glass. I don't know if it's, because it's a saying that in old buildings you can see the glass is thicker at the bottom because it has flowed. That's what people say, but it's actually wrong. Because this high viscosity, it would take more than the time Earth have existed for flow, really. So it's actually more like the craftsmen, they were hand blowing glass, and then they put the thickest one at the bottom, just to have a better construction. So the glass doesn't really flow so you can observe it. But things do flow very slowly, and this is the world's oldest ongoing experiment. Because in Australia there was Professor Parnell. He took pitch, which is almost asphalt, and you can melt it at high temperature. So he melted it, he put it in a funnel, and then he just let it be. This was 1927. And you can see that pitch is, if you get it in your hand, it's actually very fragile. If you smash it with a hammer, it will break into pieces. So you don't really imagine that it will flow, but it does. But very, very slowly. So this has dripped 9 times since 1927. So it flows extremely slow.
Still working.
It's still working. There's still more material. So now there is a live cam. It's not very exciting to watch, but but I think that they missed the 7 first drops because nobody was there. So now there is a camera. But this is like this Pantarei, everything flows. It does really flow. If you I don't know if you have bought a cheap bookshelf at home, because a bookshelf and a table, it's elastic. It bounces back immediately. But if you load it with books and leave it for 5 years, sometimes it gets bent. And then it has flowed, actually. So things flow, everything flows, but very slowly. This is silly putty. I don't know if did you have that as kids? It's like a clay, you can deform it, but if you roll it to a ball, you can bounce it. I tried to get it here, but I didn't find it. But as a rheologist, I have a box of them, of course. So I put this silly putty in a funnel and waited. So I waited 2 hours and 20 minutes. And this is 100 times speed, but you don't really see anything happen. If you have 1,000 times speed, you can see you get the drop. But it takes 2 hours, more than 2 hours. So things flow but very slowly. Okay, so shear thinning, like things like this. Most liquid foods are shear thinning. And now it gets more interesting even for a rheologist, actually. So this is a lot of information. So first, on this axis, you have the viscosity. And you can see typically water here, you have the olive oil, a plastic melt is here. So, and this is a logarithmic scale, so it's a huge difference. And there's a logarithmic scale here also. So this is the flow, the shear rate. So this is very fast, this is very slow. So sedimentation is very, very slow, right? And swallowing is somewhere here. If rubbing is here, so if you take a cream on your hand and you rub it, it's very thin, so you have very high shear rates. And you can see the oil, it's constant. So I mean, you can pass it around together with this, which is the other line. So just have a feel for how thick it is. So this is like xanthan, the thick one. And the oil is here, so oil is constant. But xanthan goes, you can see it's quite thick, right? Still, if you shear it fast, it has a viscosity lower than the oil. So it depends on how fast you shear it. If you do this very fast, yeah, then you're up here.
Oh, okay.
If you just let it be and dripping, that's slow flow, and then it's very thick. And this is called shear thinning. And the reason is this, that you have a polymer which is a long molecule. It's coiled up when it's at rest. When you force it in the flow, it will extend, and then it will align, and then will take up less space and make less resistance. And this, I will let you feel this. You can pass this back. So this is the thickener that is used for dysphagia, and this is olive oil. And if you can force this through a thin needle, but you have to push. And this is much thinner, right? Mm-hmm. Whereas the thickener, if you push that one, it's quite easy because it aligns in the flow. So give it a try. So, and the reason is that when in the thin needle, it aligns in the direction of the needle, and then it doesn't make a resistance. And then it's easy to push it. Even if it appears very, very, very different. And if you look at xanthan, which is a common dysphagia thickener, it's, you can see it's very long polymers, right? And the polymers take up very much space, unless when you push them and then they align in the flow. I told you, physics is fun, right? And I mean, two take-home messages here. Like, if you measure this, and if you just measure at one shear rate, you can get this, and then they seem to be the same, but they are totally different. So you need to measure over some shear rates. Like you have this IDSI test. I don't know if you've seen it. You have a syringe, and you let something drip out. That's really 1 point. So it's not the best. But it's probably the best you can do in a clinical setting, so it's not bad. But it's good if you can measure different shear rates. And also a practical implication, maybe not so important. Do you have like syrup here, like a concentrated sugar solution or molasses? I mean, this is what it looks like in my cupboard at home. And it's always sticky. I mean, it always sticks to the shelf. And the reason is the rheology, because if something drips, the honey or the syrup, the viscosity is constant, so it will just continue flowing. Whereas if you have something else like a marmalade, it will flow, and that will be so slow, so you're up here, and then it will stop. So that's why these always also sticky. Or if you eat a toast for breakfast, probably more common in Sweden than here, but still, and then you put honey on the toast, it will just drip through, and you will have sticky hands. So that's rheology also. Marmalade is shear thinning. So when it's at rest, very slow, it has a high viscosity. So then it stays. Shear thickening that's very unusual. You never find it in foods. And you should never find it in foods, because it will be very dangerous actually. Because if you shear it faster, the viscosity goes up, so it thickens. I think I have time to show an example of this. We made a big pool of this at the scout camp. Yeah. So this is the pool. And you can actually walk on this fluid. Because when you deform it fast, it's like a solid. And it's a very strange feeling, because if you step on a fluid, you will sink, right? But if you step on this and you continue to move, it's like walking on a solid. But if you stay, you will just sink through. And then you're sort of stuck, because then you have to be very patient and move slowly. So he's stuck. Yeah, you can see this. It's quite nice to see. And we had like 1,000 kids trying this. And we had to lift them up when they got stuck. So this is shear thickening. Never in foods, but in dispersion it happens. Like if you mix potato starch or rice starch 50-50 with water, you can feel this. It's another nice home kitchen experiment. Okay, then we come into the next one, which is yield stress. And then we have the toothpaste to remember it by. So now I talk about different things that affects viscosity. And the viscosity is like, it's affected by how fast you shear it, and it's affected by also by a yield stress. And the yield stress means that, you know, when you put on the toothpaste, it's easy to have it flow out of the tube, but when it is at rest, it stays there. And that's because of the yield stress. And maybe more common with ketchup, because if you want to have the ketchup out of the bottle, you basically have to shake it to make it flow. And that is because you have to be above the yield stress. Then it flows. But here, it's like a solid. It doesn't move. So that's typical of the toothpaste or of ketchup. And yield stress are different. And I mean, for ketchup, it's like 15 Pascal seconds. Toothpaste is a couple of hundred, so there is a lot of higher. But this is also an important thing. But you remember I said that if you wait, everything flows, right? So toothpaste should flow too, and I mean, it does. So this was a big controversy, like 1980 something. They published this paper, The Yield Stress Myth, and they said that there is no yield stress, you just have to wait. And that's true. But I mean, if you want to have the ketchup out of the bottle, you don't want to wait a week because you want to eat now. So practically, there is a yield stress. So if you look at also at the time scale, if you define that I don't want to wait a week to see if it flows. Yeah, I set the time to like hours or so. Then there is definitely yield stress. But it also means that it depends on how you measure it. But yield stress is there for all practical reasons. It makes a change for the product properties. Cement is another thing where you have a yield stress. I don't know if you ever worked with cement, but if you look at the building site, they pour out cement, and then there's usually a guy with a vibrator that goes to make it flow. And this is cement. This is in the lab. So I put it on this type of test tube vibrator that you have it in the lab. And you can see that it's actually very obvious, but because as soon as you vibrate it and it starts shearing, it flows out. And then when you stop, it's like solid again. And this is because of the yield stress. Nowadays, you can get other concrete and cement with flow properties, but usually somebody is there and have to vibrate it so it flows out. Also because of yield stress. Then there are different ways of measuring the yield stress, like in the field. If you're a construction site, you mix the cement or the concrete, then you pour it in a tube and you put it upside down. You lift the tube and then you see how much it slumps. And then you measure this side and to see is the cement or concrete good or bad. If you make tomato paste, you fill tomato here, you lift that wall and then you wait 30 seconds to see how long it flows out. And then you get like a consistency in centimeters. And this is what you have for thickeners for dysphagia, right? So you have a ring, you fill it with your solution, you lift the ring, and you see how it flows out. So since you waited a specific time, this is a function of both viscosity, yield stress, and density. So you get like a sum of all these as a measure, because you measure it like in centimeters. But it works because the yield stress is usually very low and the density is very similar. So it mainly measures viscosity.
Oh.
But if you would come up with another thickener that has a higher yield stress, it would be very strange readings. So, but you always measure a sum of a lot of parameters. Okay, then next term, to left, thixotropy is this. If you buy yogurt, it's like a pudding. If you stir it, it's more fluid. Because you usually stir it before you eat it, right? And that means that you break the structure in the yogurt. And it becomes more fluid. And this is what happens here. So these are two yogurts. So if you measure viscosity and then you stir it, this is time. The viscosity will go down. And then you put it back in the fridge and wait a while. Then the structure will regain, and then you can have a higher viscosity, and then you can do the same again. So this is time dependence, really. You have to wait a long time before the structure should reform, usually like hours. So that's a slow process. But if you break down the structure, wait, and then it comes back to the same, it's truly thixotropic. In many of these, you don't come all the way back because you destroyed some of the structure, but still, it's thixotropy. And if you buy paint, that's common. Like if you buy a paint that is all jelly when you open it, then it's because it's thixotropic, and that is because you want it to be gel-like because you don't want to have sedimentation of the dyes in the paint. So it should be stable. And then you can actually just take it directly and paint with it. And something can be both thixotropic and shear thinning at the same time. That's quite common. Because if you measure viscosity, then you often start with a slow shear rate, then you increase it stepwise, and here it's very fast. But that takes some time. So it has time to break down the structure. So when you go back, you don't go back in the same trace because you have destroyed part of the structure. And you can see this in this is a sauce, like a cheese sauce. It's the same thing. You have a structure in the starch, you break it down, you go back, and then you do it another time, then you break it down more. So this is a common test to see if you both have shear thinning and thixotropy. So you go up and down in shear rate. And also it's important to remember that temperature has an effect. So if you increase temperature, viscosity goes down. And if you imagine this thickener, so you mix it at 20 degrees, but when you eat it and if you keep it long in your mouth, you can easily decrease it to half the value. And that's because the molecules move faster at higher temperature. So it's a natural physical explanation. Now we come to the natto part. This is the elastic fluid, right? That's why I had natto. So there are other examples, but I think this is very obvious. It's important also in processes, like when you blow a plastic film for plastic bags. You melt it and you blow up a bag with air, and then it cools down and becomes a film. Then it will extend. If you have a bubble that is growing, so when you make bread, then you have bubbles forming when the dough rises. That is also extensional flow because the bubble has to extend. And the gluten protein in the bread is very good for this because it keeps the bubble without breaking, because it has an extension of viscosity that resists the expansion. But also in swallowing, right? I mean, you push something down the throat and it has to extend. This is an example. The red fluid is elastic, and this is very elastic, much more than a normal food is. And you can see that it's so elastic, so it flows over the end. It's like it pulls the fluid out. And then in this experiment, this is the same red elastic fluid, and this is Newtonian, like the oil, but they have exactly the same shear viscosity. But this is like elastic and slimy. So which comes out first? Well, the Newtonian one comes out much faster. And this is because you have vortices forming in this. So it sort of pulls the fluid with it. So it pulls it here. So it just goes round and round in the corners. And that makes a resistance to the flow. So that's why this one is slower. And I don't know if that has an effect on swallowing, because the foods that are elastic, like this thickened fluid, it's not so elastic. So I don't think it affects the time. But the other good effect with elasticity is that it keeps drops together. So like when you swallow something, it keeps the bolus together. So it doesn't break up in small droplets, which is good if you aspirate, for example, then it prevents that in the fluid properties. And then you can measure this as well. You use the same equipment as I showed you before, but in this case you don't rotate, you oscillate. And when you oscillate, you get the response both from the elasticity and from the viscosity. And then as a result, you get the modulus, which is called elastic modulus and viscous modulus. So you get two measures of this. I'll go briefly through this, because this is more than what you will ever come into in this area, I think. But the usual example is again this silicon putty that bounces. So if you do a fast deformation, now I've filmed this in slow motion, this clay will drop and it will bounce like a rubber ball because this is very fast and then it acts as it's elastic. If you just leave it on the table, now I did the time lapse, so this is like almost an hour, and then it will slowly flow and settle out. So this is typically viscoelastic because it has both this viscous appearance and the elastic one. And you can do a measurement where you measure these two moduli and you change the frequency. And you call it a mechanical spectrum. It's like a light spectrum, really. You change the frequency. So if you do something fast, let's see, or then it bounces. So high frequency is like fast. And then this elastic modulus is much higher. If you do it slow, it's a viscous modulus that is higher. So by this characterization, you can see if a material is viscoelastic, how viscoelastic it is. If you take like where they cross, that's a typical relaxation time. So this one will take like 1/1 second or 10 seconds maybe to relax. So you can get the typical relaxation time of a material as well. So this is common way of measuring viscoelasticity when you have something that is more or less equally viscous and elastic. And I think I just have one slide left. Yeah. You can find this in foods as well. And this is one of the nice restaurants you have taken me to. And they had a very viscoelastic dessert. You could say slimy. This was, I mean, it was very obvious viscoelastic. So it was, I think this is a very good example. It tasted very good.
Yeah.
Yeah. So, yeah. I think that's what you say in Japanese, right? Yeah. Pleasantly slimy.
Never.
Yeah, we don't have a word for that, so I have to use the Japanese one. So with this, if you, I have written this in like an online textbook. If you want to go back and look at this, you can find it in the textbook. I can send out copies also if you like of this, so you have it. Because I expect you all study hard, because on Friday we have an exam. No, we're not. It's fine. But this is more like if you want to, if you get rheology in a paper or something and you want to look up a term, this is sort of an easy description. So thank you for your attention and for playing along with all the fluids. So it was nice to have the possibility to talk about rheology.
Thank you very much.
Mm-hmm.